Hi, my name is Denzel Carter, and this is Lab 3, Magnetic Field of a Bar Magnet. So in this lab, our purpose is to find the distance dependency of the magnetic field due to a small bar magnet and use Biot-Savart's law. Here are the materials below. So the fundamental principles I used were the Biot-Savart law when the distance away is much greater than the radius of the magnet. The magnetic field of the bar is found by K times R to the N, where K is a combo of the constants of magnetic moment and N is the distance dependency. The equation for the code is below. So the procedure for this experiment is to align the phone north to south and then run a meter stick below, running east to west, and then find the magnetometer sensor on the phone and place tapes marking that location. So the second part of the procedure is to move the phone east to west with it pointing north to south, finding the distance from the magnet where the magnetometer measures 20 microtesla, 70, 120, 170, and 220 microtesla, and record 3 charls for each. And then take an off-axis measurement where you take the distance where 100 microtesla is measured and then move that direction in the y, where the net magnetic field is 100 microtesla, and move that distance in the y direction and then record the x, y, and z components. So here's the data I found on the right, and the findings I found for this were that when the magnetometer is far from the magnet, a near zero x component is measured, and as the magnetometer moves closer to the magnet, the x component increases. Here's the second part of the data where on the right you can see my chart, and the line of best fits equation is shown at the top. The equation that I used to solve for K and N is shown, where the ln of the magnetic field in the x is graphed versus the ln of r. And this equation allows me to find ln of k as the intercept and n is the slope, where the distance dependency n is about -3, which is what we'd expect. So here's my calculations, the distance dependency, where the magnetic field of the bar is basically mu naught over 4 pi times 2 mu over r cubed. And to find mu, we first have to find k, where we take e to the ln of k, and then k is equal to mu naught over 4 pi times mu from the on-axis approximation if r is much greater than r. And then mu I found to be 4.32 amperes times meter squared. So measuring the off-axis magnetic field, you can see my measurements at the top showing the x, y, corrected y, and z components. The experiment measurements and the glow skirt measurements are also below. And when you compare the two, you can see some discrepancies, which can be explained by the assumptions on the next page. So here's my code I wrote for my glow skirt model. On the left, you can see where I created the function for the magnetic field. And on the right, you can see how I created the arrows. Here are the assumptions I made on the left, where the computational model is going to be ignoring the Earth's magnetic field. The magnetic field from objects in the room is also ignored that may disrupt the magnetometer. And I've also assumed that the smartphone magnetometer is accurate and the sensor was accurately found. On the right, you can see my glow skirt model where the blue arrows represent the perpendicular field. The orange represents the parallel or on-axis field, and the pink represents the off-axis field. So my reflection questions for this experiment: what if I hadn't compensated for magnetic north and just laid out the meter at some other angle? This would affect my results because in the x direction, the magnetic field would now include the magnet's magnetic field and the Earth's magnetic field, and so I could not find a distance dependency of 1 over r cubed. And basically, at the beginning of the experiment, we had to find the magnet to be orthogonal to the Earth's magnetic field so that the x component would not be affected by the Earth's magnetic field. If I were to stick two identical magnets together end to end and redo the experiment, I would find mu to be nearly double, as there would be almost twice as strong of a magnetic field created by the two, but not completely double, as the further magnet would not have the same effect as the closer magnet if they were stuck end to end. And I would still find a distance dependency of 1 over r cubed, but the distance to find the same magnetic fields would be about 2 to the 1/3 power. Thank you.